Okay, so this is Math Step 341, Lecture 9, and what we're going to be doing today is talking about trump splits, conditional probabilities, Bayes' theorem, and stuff like that. If we have time, we'll do a little bit on inclusion, exclusion. One of the things I really want to emphasize, and there's a section in the book on this, is how to sniff out formulas. So we've already done this a few times. We've looked at, trying to find, things such as the product rule or whatnot, looking at some special cases, trying to build some intuition and get a sense of what the answer is. What we're going to look at today is going to be, a very standard formula. You may have already seen it before, but it's the general principle that really matters is how do you look at a new problem and try to get a sense of what the answer may be. General items, as always, if you're unsure if your answer is right or wrong, run simulations. So I'm going to modify the code slightly from what's in the book. But again, if you can calculate something in more than one way, do so. Hopefully the two will match. If they match, does that mean you're right? No. But you have at least a little bit more confidence. If they don't match, at least one of them is wrong. And one way to try to get a sense of whether or not you've dropped a factor or whatnot is to run some code and get a sense of whether or not it's right. The next item that I really want to emphasize is the importance of phrasing. Depending on how you phrase the problem, it can be interpreted different ways. I think I might have shared the story about when my father was at a party and he talked about how his wife had a son from her first marriage who is now in college, which was also a son from her only marriage. But the way it was phrased, it led people to interpret things very differently. Be very careful how things are phrased. In mathematics and statistics, we are hopefully trying to phrase things in such a way as to make it very easy for people to understand. But a lot of times, standard English is not the same as what a mathematician or a lawyer might mean by a phrase. So be very aware of stuff like that. And then as always, just the importance of exploring extreme cases. If you take, well, what if I consider this extreme case where this is the whole set or this is nothing or they're the same? You can often build a lot of intuition by looking at that. Okay, so what I want to calculate first is what is the probability we have a 5-0 split in trump? So out of curiosity, how many people know how to play either bridge or whist? So, speaking of which things survive and don't survive, certain games are no longer as popular as they used to be. So your bridges, I think one of the more interesting card games, and in certain tournaments in duplicate bridge, you actually can play with a deck of cards and teams so that there is 0 luck, because each team is 4 people, and so you play 2 hands as north-south and 2 hands as east-west. So you actually have both sides of it. You deal out the cards, so standard deck of 52, and you typically bid on which suit is going to be trump, spades, hearts, diamonds, or clubs, or if you want there to be no trump. So obviously, if there's a trump suit, the more trump you and your partner have, the better it is for you. And a lot of times you want to know how are the non-trump distributed among the other players. Let's say there's only one non-trump out, and you have 2 opponents. What does the distribution have to be? So you have 2 opponents. Well, everybody gets 13 cards. You and your partner have 12 out of the 13 trump. Opposition has 1. What must your split be? 12-1. You have 12, they have 1. But how is that 1 distributed among the 2 hands? 1-0. Right? There's no uncertainty in that. You don't know which one of them has the trump, but you know it's a 1-0 split. What if there are 2 trump out? How could it be split? It could be 2-0, or it could be 1-1. And it starts to get more and more interesting. So a lot of times it's really bad the more trump are in someone's hand in opposition, because they can then protect their trump and make it good later. Whereas if the trump are more evenly split, if you play your boss trump, you actually kill 2 of the opponent's trump at the same time. So one of the worst things would be, one person has all 5 remaining trump. And so we want to calculate what is the probability that, if I have 8 trump between myself and my partner, that the 5 missing trump are all in one hand. And so again, we have 13 cards in the hand. So 4 hands of 13, partner and I have 8 trump. We are missing 5. And so how could we have all 5 in one hand? Well, we first have to choose which opponent has the 5 trump. How many ways can we choose which opponent has the 5 trump? 2. 2 choose 1. So I want to be as pedantic as possible. 2 choose 1. So I'm choosing who has the trump. So which opponent? All right, now, what do I need to do? I have to give them the 5 trump. So how many ways can I give them the 5 trump? Think. I've got 5 trump, and I have to make sure that they choose all 5 of them. How many ways are there to do that? Why 5 choose 2? Well, I've already chosen which opponent is getting all the trump. It's just 5 choose 5. I have 5 trump. They must choose all 5 of them for their hand. So it's 5 choose 5. Get all the missing. Now I have to fill up the rest of their hand. How many cards are there available to fill up their hand? So my partner and I have 13 cards each. That's how many? 26. How many of those 26 cards are still available? I'm sorry? 21. So there are 21 cards left. And how many must I choose? 8. So it's 21, choose 8. Fill up hand. Now, let's be exceptionally pedantic. How many cards are left? 13. And I have to choose 13 cards for the other person. How many ways are there to choose 13 cards from 13? 1. Or 13 choose 13, right? Yeah. 13 choose 13. Other hand. And then what should I divide by? So I now want to form 2 hands of 13. So how would I choose the first hand? So 26 choose 13. First hand. Times 13 choose 13. We've got to be very careful about, are we introducing order or not order? I start off by saying which opponent. So I have first opponent, second opponent, and I've got first hand, second hand. So this looks good to me. So this is one way to calculate the probability that one person has all 5 missing trump. Another way is to assign the trump one at a time. When I have the first trump, and I have my 2 players, what's the probability I give it to player 1? 50%. What's the probability I give it to player 2? 50%. So I have 2 choose 1 ways to choose who gets. And in the first trump, it's a 50% chance, right? Yeah. So how should I view the 50%? I'm going to view it as there are 13 spots in my hand, and there are 26 spots total. I need to choose one of those 13 of 26 spots to give it to player A. So it's 13/26 for the first spot. Now, so the way I'm looking at it, I'm going like this. So I first put it in one of the spots here. Now, how many spots are available for the first player? 12. How many spots are available total? What's the probability you get it on the second one? So 12 over 25. What's the probability on the third? 11/24. And then 10/23, and then 9/22. And I believe These are both equal to, is it 9 over 231? Over 230. Yes, it's 9 over 230. And there's another way to do this. Or there's two choose one ways to choose the person. And what's the probability each trump is in a given hand? 50%. So each trump has a 50% chance of being in a person's hand. So it should just be times 1/2 to the 5th. 1/2 to the 5th is 1 over 32. So this is 1/16. And they're not equal. So we've got 3 methods. 2 give the same answer. 1 gives a different answer. This is about twice as large. Thoughts? So we could simulate it. And so 1 divided by 16 is about 6.25%. 9 divided by 230 is about 3.91%. So before we simulate, any thoughts as to which one is probably right? The first one. Why? What's the mistake I'm making in the second?
Is it the sense we're saying 1/2 of it, you're assuming with
Yeah, I'm basically assuming that I keep having the same probability of 1/2. Imagine the ridiculous situation where I only had 4 cards left in my hand to fill. I can't put in 5 cards. This should break down at some point in some extreme setting. So again, this is the power of looking at extremes. I can't believe this is going to keep holding. And as I fill up more and more spots, it should become harder and harder and harder. That's why I like this argument over here of looking at how many spaces do we have. We will later look at an argument similar to this when we get to the very famous marriage or secretary problem, depending on how you want to phrase it. This is one of the most dangerous problems in probability. One of my students has promised to choose his mate this way and is still single. So be very careful when we get to that lecture. So simulate is the way to go. And so I tweaked the code a little bit from last time. In the interest of space, I'm not putting up comments. Again, my deck, I'm going to choose 5 of the numbers to be 1 and all the other ones to be 0, because I only care about is it a trump or not a trump. So I don't really need to store all the information about the deck. I'm going to do some number of times. And what I'm going to do is I'm randomly going to sample 13 cards to form a hand. And I'm going to see if the sum is either 0 or 5. Or instead of more generally 5, I just number of bad. Yeah, so I can have that either be 5 cards if I want a 5-0 split, or if I want an 8-0 split, I can trivially tweak the code. There's no reason to hardwire a number like 5. Make it a little bit more general and do it like this. This is a nice, clean way of saying, is it 0 or num bad? I'm just saying mod means if I take this number and I divide by this, is the remainder 0? So that means it's either 0 or num bad. It's just a little bit faster way of doing it. And so when we did 1,000,000 times, we got 3.94. When we did it 10 million times, we got 3.913. And 9 divided by 230 was 3.9130. So it's looking pretty good. This is extremely compelling evidence. What's nice is the 2 probabilities are well separated. And so when you do the simulations and you're seeing it's really agreeing with 3.91, you're pretty confident that you've nailed it. Okay, and we've seen why the argument has issues. Okay. So one of the greatest bands of all time, ABBA. I've heard that they're actually getting back together and touring. Is this true? Okay. So here are 2 statements. I'm going to form a group of 2. In the first way, Each person is equally likely to be chosen, and I'm forming a group of 2 people from 4. In the second, I'm going to choose any group of 2 people. All groups are equally likely to be chosen. Are these 2 statements equivalent? So have I just basically said the same thing 2 different ways? No. Why not?
Because you can have each person be like you chose, but not each group.
Good. So anybody know the marital history of the people in Alba? So it depends on what you mean by 2. What do you mean by 2 in divorce?
There were 2 couples.
There were 2 couples, and both couples divorced. So in a situation like that, you could reach the situation where you might say, you know what, I've got enough money. I really have no desire to get back on the road and tour with my ex. So I will write it as A sub 1, B sub 1, I'm sorry. B sub 2, A sub 2 to indicate who is married to whom. Okay. I guess I could have written the B's backwards, but that doesn't work as well for the A. All right. So now let's consider forming groups of 2 such that you cannot be in a group with your ex. So we could have A1, B2. We could have A1, A2. And again, I'm going through in a nice methodical manner to make sure I don't miss any cases. I'm not just going willy-nilly and randomly choosing things. I'm going, I've got A1, I can't do B1, let's do B2. I've got A1, I've done these 2, let's do this one. What do I start with next? B1. And who can B1 be with?
A1. Oh, no.
So we've already done A1. So we just keep going to the right. So B1 can be with B2. B1 can be with A2, right? And B2, A2 can't be together because they were married. So I have 4 sets. How often is A1 here? Yeah, each person in 2 of 4 or 50%. And we never have A1, B1 or A2, B2. Right. But here, I do have a situation where each person was equally likely to be chosen, but it's not the same as each group is equally likely to be chosen. So you've got to be careful about the phrasing that you say. Okay. So let's look at rolling fair die. And in case you did not know this, there are actually a pair of fuzzy die hanging in the Millennium Falcon. Han Solo has a lot of cool moments. You know, the fuzzy die is something many of us know. So if you have 2 fair independent die, that means the roll of one has nothing to do with the roll of the other. Each one gives you the numbers 1 through 6 equally likely. What is the probability if I roll 2 fair die that the sum is an 11? Two 36s? I can get a 6 and a 5 or a 5 and a 6. So we all agree that this is 2 36s? This is 2 36s or 118. What about the probability that the sum is a 7? So what is the simplest way to see that it's 636? Well, one way, of course, is to just enumerate all the possibilities and see that there's 6 of them. So it's 6 out of 36. There's a faster way to see that it is 6 out of 36. What is 6 out of 36? Imagine you roll something on the first die. Not only is there always a chance, what's the chance that the second die gives you a 7? It's 1/6. It doesn't matter what you roll on the first die. There's one and only one number on the second die that will add up to 7. So it's just 136. So now what we're going to do is we're going to turn to conditional probability. You know, not all conditional probabilities are this easy. Given that the first die is a 3, what is the probability that the sum is an 11? 0. Right? Given that the first die is a 3, what is the probability that the sum is a 7? 1/6. So what we notice here is that sometimes the conditional probability is the same and sometimes the conditional probability is different than the probability. So conditional probability can be the same or different as the probability. So the question is, for conditional probability, if I give you some additional information, how does that affect your assignment of the probability that something happens? So can somebody give me an event that's a conditional probability? Where I'm giving you some information and now I want to know, given that information, what's the probability that this happens?
I get my hair cut, I don't feel bad about myself.
Okay, so good. So if you get your hair cut, the probability you feel bad about yourself. Now the question is, who's cutting your hair? Bad barber. And so if I know that bad barber is cutting your hair versus a good barber is cutting your hair, should that impact the assessment of what is the probability he is going to feel bad about himself? Assuming that you actually care what your haircut looks like. If you're trying to calculate what's the probability that someone is going to win a game, if I tell you certain players are injured and not starting, that will greatly affect the probabilities. Or somebody is pitching versus not pitching, greatly affects the probabilities. So most things in life are actually conditional probabilities. I want to calculate the probability that something happens given all of these other things that I know. The question is, we don't always know all of these probabilities or all these values. All right. So we want to try to find a formula. We're going to write the conditional probability as the probability of A/B. So this is the conditional probability of A given B happens. And we actually are going to make a little bit of an assumption. What might you want to assume about the probability of B? It's non-zero. Because if I want to talk about what's the probability of A given that B happens, if B doesn't happen, then A, so we get into a situation where I don't really want to talk about this. What's the probability that you will pass this class given that Professor Miller is now rooting for the New York Yankees? I am not rooting for the New York Yankees. There is no, it's not even worth discussing something like this. Mets, I'm happy to root for. I've got students who work for the Mets. Although you should watch the Futurama episodes about the Mets. So if I tell you that B happens, sometimes that should affect your options of the probability of A. So we want to try to find a formula. And the simplest possibility is a formula that depends only on the probability of A and only on the probability of B. So the question is, could we find a formula that depends on just these two bits? Can anybody think of some interesting cases for A and B? So you could try, give me some interesting A's and B's. Okay, so B would be, that would be B is the entire space. B equals omega the entire space. So the probability of B equals 1. What should be true in this case? Yeah, because if B happens with 100% certainty, then this should imply the probability of A given omega is just the probability of A. Okay. What's another interesting case to take? You got to give me an interesting pair A and B. Good. So we could try, if A equals B, then the probability of A given A is just, it's 1, right? Given that A happens, what is the probability that A happens? Right? 1. There's another interesting case to take. A is B complement. If A is B complement, you want the probability that A happens, given that A doesn't happen. So what's the probability that A happens? Yes, it's just 0. So now I want a function that depends just on the probability of A and just on the probability of B. Now, if A equals B, it's got to return 1. And if A equals B complement, it has to return 0. Can anybody give me a good value for the probability of A and B complement? So what would be a good probability to have for them? So I've got 3 events, A, B, B complement. So, but I want the probability A and the probability of B in this case to be the same as the probability of A, probability of B in this case. So I want, if A equals B, I want the probability of A and the probability of B to be the same as if A equals B complement, and I have the probability of A, the probability of B complement. I'm sorry. I guess I call it A complement. So what would be a good choice for the probability of A, B, and B complement? There's one good number where these pairs are going to be the same. 0.5. Take probability of A equals the probability of B equals the probability of B complement equals 1/2. So in a situation like that, I would have the special case where I would have f of 1/2, 1/2. So we would have f of 1/2, 1/2 equals 1, and f of 1/2, 1/2 equals 0. No such f exists. Because if the probability, the conditional probability depends only on the probabilities of A and B, then if I take the special case when A equals B and both happen half the time, I get 1. If I take the special case when A equals B complement and they both happen half the time, I get 0. So there can't be any function that depends only on the probability of A and the probability of B. Conditional probability has to be more involved in this. And what's great is we proved the non-existence of a formula just by looking at some extreme cases. Okay, so we haven't proven what the formula is, we've just proven what it is not. Okay. So we want to try to find a more involved formula. It's going to depend on the probability of A, the probability of B, and let's add something new. Let's add the probability of A intersects B. So this means A and B happen. And so we've got a couple of extreme cases. The probability of B given B is 1. The probability of B complement given B is 0. And the conditional probability has to be between 0 and 1. So it turns out that there's a nice expression that will satisfy all of this. And so what we have is, let's try the probability of A given B is the probability of A intersects B over the probability of B. And again, if we try the special cases, it satisfies all these cases. Satisfies the 3 points above. If A equals B, we get 1. If A is B complement, we get 0. And the probability that A and B both happen can't be larger than the probability that B happens. And so it's going to be strictly between 0 and 1. It makes intuitive sense. I mean, what's really going on here is, imagine this is omega, Here is B. And then here is A. And then over here, this would be, this would be A intersect B. And so when we say B happens, we restrict ourselves to living in just the red region. And then if we want A to happen, given that B happens, that's this region over here. What we're essentially doing is we're rescaling the probability so that now we rescale so that the probability that B happens is 1. So we're essentially just multiplying by 1 over B. Okay. One way to try to gain intuition about questions like this is to just roll up your sleeves, do some calculations. One of the things I like is the expected counts approach. So here's the problem. Suppose you go out fishing one day, and you have the following set of rules. You stop fishing once you catch a fish, or after you've been on the water for 4 hours, whichever comes first. So I'm going to keep fishing until I get a fish. And if I don't have a fish after 4 hours, I go home. And let's imagine that there's a 40% chance to catch a trout. So we have 40% chance catch a trout, a 25% chance we catch a bass, and a 35% chance catch nothing. Okay. Are those reasonable probabilities? Why are they reasonable? Yeah, they add to 100. Something happens. You either catch a trout, a bass, or nothing. And then the question is, imagine we know that you caught a fish. What are the odds that you caught a trout? Yes.
So is the probability of not catching a fish 0? Being on the water for 4 hours?
No, it's 35% chance that we catch nothing.
Oh, yeah.
Right? So the probability that we catch nothing is 35%. But now I tell you we caught a fish. So now you know it goes through. Yes. Right, so what would be the probability? The probability that we catch a trout given that we caught a fish. So probability of a trout given caught a fish. And what do you think that should equal? 0.4 over 0.65. And so one way to see this is what's called the expected counts approach. So let's imagine we do so many iterations of this. You want to choose a nice number that's going to split evenly when you multiply by all the probabilities. So I don't have to do a number as large as 1,000, but I see a couple of decimals that are multiples of 5. If I start up with 1,000, let's do 1,000 days. In how many of those days do we catch a trout? 400. How many of those days do we catch a bass? 250. And then how many do we catch nothing? 350. So now, if we look about the case where we caught something, so we see 650 times caught something. 400 of those are trout. So it's 400 over 650. And this is just another way to see the reasonableness of what we're doing. Okay, so again, when we're doing these items, if I have a set A and A complement and B complement, there's 4 possibilities. I have A and B. I have A doesn't happen, but B does. I have A happens and B doesn't, and I have neither happens. And so the conditional probability, as we said, is the probability of A given B is the probability of A and B happens divided by the probability that B happens. And I'm assuming that the probability of B is greater than 0. The reason I want to assume the probability of B is greater than 0 is you really shouldn't be talking about what is the probability that A happens, given that B happens when B doesn't happen. No. So this will give us a 0 over 0. So we can rewrite as the probability that A and B happens is the probability that A happens given B times the probability of B. So this is just another way of rewriting the above. What's nice about this way of rewriting? So you can solve A intersects B, but there is something nice about writing things this way. Yeah, when I write it like this, I don't have to worry about dividing by 0. So when I write it like this, there's never division by 0. Now, what happens if the probability of B is 0? Well, so is the probability of A intersects B. So that would be 0, that would be 0, and this would be undefined. But the equation at least makes sense. You know, I have 0 equals 0. So this is one way to write it. So if we can calculate the probability that A and B both happen, and we can calculate the probability B happens, then we can calculate the probability of A given B. We can calculate the conditional probability. If I know the conditional probability and I know the probability B happens, then I can actually get the probability that A and B happens. So depending on what you're given, one formulation is sometimes more useful than the other. You can use, if you know 2 out of 3, you can use it to figure out the third. It's like, you know, when you have 2 angles of a triangle, we know what the third angle is going to be. One of the places where this is used is inclusion exclusion. So it gets harder and harder when you have these Venn diagrams, when you have more and more sets. 1 set, 2 sets, 3 sets is not so bad. Getting up to 4 sets becomes really tricky. So we're going to just confine ourselves to 3 sets. So we have a space omega, and I have, let's say, 3 possible outcomes that I care about: A1, A2, and A3. And I might care about maybe both A1 and A2 happen. So that's going to be the region up here. Maybe I care about A2 and A3 happening. That's the region over here. A1 and A3, that's the region up here. But then I could also care about the region when all 3 of them happen, which is the intersection. And so given various events, I can assign oftentimes probabilities to different things. So maybe A is the probability that you are, you know, a math major at Williams College. And maybe that's A1. Maybe A2 is the probability that you've taken a stats course. And maybe A3 is the probability that you are on a sports team. And I could ask, you know, what are the probabilities? So is every math major going to have taken a statistics course? No. So this is not going, they're not going to be subsets of each other. And I can see, you know, just exactly what would these different probabilities be. And so if I want to try to calculate what is the probability of A1 union A2 union A3, you know, how would I start calculating probabilities like that? We want to be very careful about double counting. So what is the probability of A1 union A2? It might be, you know, the probability of A1 plus the probability of A2, but then what do I have to do? Subtract off the probability of A1 and A2. So if I have, you know, here is A1, here's A2, here's this double counted region, which is A1 intersect A2. And so if I want to know what is the probability of the union, I always want to reduce things to simpler calculations. It turns out intersections are much easier to study than unions. If you want to know what's the probability 2 things happen, that's usually not too bad. If you want to know what the probability of a union is, that's a little bit worse, and that's the inclusion exclusion. If I now want to go back and say, well, what's the probability of A1 union A2 union A3? Okay, so these regions, which just labeled A1, A2, A3, those occur by themselves. Then the regions in You want to say that's a golden yellow? Goldenrod? I don't know. We have to subtract all of those. But when we subtract all of those, how often do we subtract this region in here? 3 times. But we already counted it 3 times in the A1, A2, A3. So then we have to add it back. So we would get the probability of A1 union A2 union A3. Oops. Is going to be the probability of A1 plus the probability of A2 plus the probability of A3 minus the probability of A1 intersect A2 minus the probability of A1 intersect A3 minus the probability of A2 intersect A3. And very similar to ABA, you see how I'm going through it very carefully to make sure I don't miss anything. And then we have to add back the probability of A1 intersect A2 intersect A3. And that will be the probability of the unit. And what you can do is you can imagine an element in different places and see how often is it counted. So as a check, imagine X is in A1, but not in A2 or A3. So if X is in just A1, I count it once from the probability of A1, and I don't count it any other time. Now imagine you have an X that's in A1 and A2. I count it once, and I subtract it once from A1, A2, and then nothing else doesn't matter. So if something is in just A1 and A2, I've counted it twice, I've removed it once, good, it's a net count of 1. If it's in all 3 of them, I count it 3 times, then subtract it 3 times, and then add it back once for a net counting of 1. So this proves that I've counted everything once and only once, at least for the things that are in A1, A2, or A3. If it's not in A1, A2, A3, it's not counted at all, so there's nothing to worry about. So the more general inclusion-exclusion formula is the monster here. And so sometimes instead of talking about the unions, we sometimes just talk about the cardinalities of the set, if we're looking at finite sets. And then the probabilities would just be dividing by the number of possibilities. So if I have the union of the AIs or the probabilities, we can just put a probability in front of all of them. I first take all the sets individually. Then I subtract off all pairs. So I'm going to do 1 less than or equal to I, strictly less than J, less than N, or equal to N. Because if I equal J, then AI intersect AJ is just AI. And I want to talk about pairs of sets. And then I have to add back all the triples, then subtract off the quadruples, and so on and so on. This is actually a beautiful formula, and it allows you to estimate a lot of probabilities. You can get upper and lower bounds depending on where you stop. Oftentimes if we stop over here, we've stopped just before a minus, it might be an overbound. If we stop over here, it might be an upper bound. It depends a little bit what the probabilities are, but you can often make this rigorous. So the question becomes, why is something like this true? And so, here is our formula. So how many ways can we have? So let's do the special case. All the AI are the same. All the AI intersect AJ are the same, and so on and so on. This is a really nice special case. How many ways are there to choose an index I from 1 to n? I'm sorry? There's n ways to choose it, but I don't want you to say n. N choose 1. So there's n choose 1 way, right? How many ways are there to choose 2 indices from 1 to n? I'm sorry? And choose 2. What's next? And the pattern continues all the way down to plus -1 to the n minus 1 and choose n. We've chosen everything. Does this look like anything you've seen before? It's not a Taylor series. Where have you seen something like this? Yeah, this looks a lot like the binomial. So what I'm going to do is I'm going to subtract off n choose 0 and add n choose 0. So we're adding 0. Am I allowed to add 0? Yeah, and so if I add 0, I get n choose 0 minus n choose 0 minus n choose 1 plus n choose 2 minus dot 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 plus negative 1 to the n and choose n. This is, well, what's n choose 0? 1. Now, what is the sum? But what is the sum? What is n choose 0 minus n choose 1 plus n choose 2? What does that sum equal? So if you don't know, what should you do? How would you conjecture what that sum equals? What would you do? Try it out. So give me a value of n and I will calculate it in my head right now for you. 0. 10. 0.
374.
Can we do 373 instead?
Yeah,
0.
0.
What do you conjecture based on this evidence?
Equals 0.
This is just 1 minus 1 to the n. When you use the binomial theorem, this is the binomial theorem, with x equals 1, y equals negative 1. So the answer is just 1. So this is basically saying we've actually counted for everything when we do the inclusion exclusion like this. That the number of times we're throwing things away, it all balances out. Now, what's particularly nice is it simplifies when we assume the equalities above. So when we assume that, we then get the probability of A1 union AN is equal to n times the probability of, say, A1 minus n choose 2, the probability of A1 intersect A2, because they're all the same, plus n choose 3, probability of A1 intersect A2 intersect A3, minus dot 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 plus negative 1 to the n minus 1, n choose n, probability of A1 intersect all the way up to AN. So in the special case, when they all have the same probabilities, it allows us to calculate these extremely quickly. And so in the next lecture, or in the book, we'll start looking at some special cases. And so some of the cases might be, I want to calculate what's the probability that there's a perfect deal in bridge. So perfect deal means somebody gets all the same cards in the suit. How could somebody get all the same cards in the suit? You have 13 cards. So you have to, how likely do you think it is for someone to get all the cards in one suit? So there's 52 choose 13 ways to choose 13 cards for one person. 4 choose 1. So you have 4 choose 1 ways to choose the suit. Okay, so we got to be very careful how we do this. So you could choose the suit, 4 choose 1. Then you choose 13, choose 13. But there's a problem with this argument. It's unlikely. Who wants to be the lucky person? Okay, you were dealt all the spades. Is that the only way when I'm dealing with the cards that somebody at the table could have all the cards in one suit? What else could have happened? So somebody else could have had. So now, as lucky as you were to get all the spades, To have someone else at the table have all the hearts would be phenomenal. To have everybody at the table be one suited would be phenomenal to such an unbelievable level. It's actually been reported as happening a couple of times. Now, when you see a report like that, my probability book when I was an undergraduate said, let's look at the probability that just 2 out of 4 people at a table would dealt all cards in a suit. That would be far more likely than all 4 people. And there's been no reported cases of that happening. But there's been reported cases of everybody being dealt all of a suit. So either the cards are not shuffled or something else, you leave that too. But you would want to use an inclusion exclusion. What's the probability that at least one person has all the cards in the suit? I would calculate what's the probability that I have all of one suit, or you have all of one suit. Player 1, player 2, something like that. All right, so that's a good inclusion exclusion. We will stop here and we will continue this in class.